All right, so quick review so that we don't get messed up when we go to this next topic. We said quality is equal to mass of the vapor, of the steam, divided by mass of the liquid, or water, as I said last time, plus mass of the vapor. And when I have all vapor, if I had 100% vapor, we say quality equals 100%. When I'm a saturated vapor, the G point, saturated vapor, or the G point on our TS curves. And we also know that quality equals 0% when I'm at the saturated liquid point, because I'm still all water. I haven't commenced vapor production yet. And that's the F point. Well, another way of looking at this is the moisture content. Moisture content. And we're going to denote that as MC. A lot of times, that's a bad M. I'm going to rewrite that. A lot of times in reactor theory, we have several symbols that we use M. So I'm going to use MC just to remove confusion here. Now, in the book, it uses an M. But it's equal to moisture content, M or MC, is going to be equal to, check this out, mass of the liquid divided by the mass of the total. So that's mass of the vapor plus mass of the liquid. So another way of saying this, if I was at the F point, moisture content, it's all water. I have 100% water at the F point. Moisture content, I'm starting to go off the table here. Let me erase that. Moisture content, I'll come up here. Moisture content, when quality is 100%, is 0% because there's all vapor. Moisture content, when the quality is 0%, means you have all water. So the moisture content is 100%. So X equals 1 minus MC, moisture content. So you only have 100% of liquid water. If it's all water, you have 100% moisture content. If you have all steam, it's 100% quality. And we know we like to send 100% quality steam to our spinning turbines to ensure we don't have impingement damage on our blading. So continuing on, that's moisture content. If you take all of the water and all of the steam, it's got to equal 100%. So anywhere along the line, if I picked here, we know that there's a high moisture content down here and very low quality. Once I get all the way up here towards G, I know I have lots of steam, high quality, right? So I initially had showed you an equation. Well, we're going to come up with some more equations. I showed you an equation to figure out enthalpy of a subcooled liquid down here. I'll just tell you, we could have figured out using the same equation, the specific volume of a subcooled liquid or the entropy of the subcooled liquid using the same form of the equation. And we knew that it existed, those all existed at levels below the F point. Next thing we're going to talk about is levels that exist above this point here. We've been talking about superheat. Superheat. Superheated region. That's the superheated region. Once I passed this point, from here down was subcooled, from here over is superheated, and right in the middle is a mixture of water and steam as I'm adding energy. And we have an equation. And now let's say this TS diagram, and this was atmospheric pressure. I know that this is occurring all at 212 degrees, and that this down here was something less than 212 degrees. It resulted in a sensible heat addition, and then the constant vaporization of water at 212 degrees, and then boom, I see a temperature increase. I see 213 degrees. I have superheated this water above the saturation temperature for atmospheric pressure. That's pretty cool. So we have both on that page, we have both a A knowledge requirement says define moisture content. Moisture content, define it, and we did. And now it defines saturated vapor. Well, this is a saturated vapor, and any steam that exists above the temperature right there of a saturated vapor is going to be called a superheated vapor. And I had to have another equation. I already know this is superheated right now. It's superheated. It's above saturation, and that's what superheat is. You have raised the temperature above the saturation temperature for the existing pressure. You have superheated it, and in this case, I've superheated by 1 degree because I'm existing at 213 when the saturation is 212. There's the equation then. Superheat in degrees Fahrenheit is equal to, well, it's equal to the actual temperature minus the saturation temperature. So how many degrees of superheat do I have in this case? Well, the actual temperature is 213 degrees Fahrenheit minus 212 degrees Fahrenheit. I have 1 degree Fahrenheit of superheat. If I continued to raise the energy level way up here such that it was 272 degrees Fahrenheit, well, I would come here, just replace that actual temperature that exists now as 272 degrees Fahrenheit, and I can see that would result in 60 degrees of superheat, 60 degrees above the saturation temperature. Superheated vapor can carry a lot of energy. We don't generally see superheated vapors in the boiling water world except in a few places. So keep that in mind as we move forward. And we're going to learn in this book that we have superheated tables. Superheated tables are in the back of this book. So we'll get to use the saturated steam tables and the superheated tables, but there are no subcooled tables in that book. So we're going to have to learn a trick. We'll learn a trick.